Welcome to Chapter 2, Chemical Principles. In this chapter, we're going to be covering objective number 1, which is to provide students with the fundamental knowledge of biochemistry to understand later topics of microbiology, such as microbial genetics, microbial nutrition, enzyme function, and so on. But in this chapter, we're going to focus on a fundamental knowledge of biochemistry. Because this is a big chapter, we're going to split it into two. In the first part, we're going to focus on atoms and orbitals, bonds and attractions, and chemical reactions. In the second half, we're going to cover water and organic molecules. An atom is the smallest part of an element that still behaves as an element. For example, an atom of oxygen still behaves like oxygen, even when you've pared it down to just an atom. Now, atoms come in three parts, three subatomic particles. The first one is the proton. It has a positive charge and it has a mass. We say that it weighs 1 atomic unit, or AMU. An AMU is basically defined as the weight of a proton. On our diagram down here to the right, the proton would be in the center of the atom as a part of the nucleus. Neutrons are also a part of the nucleus, and they have a charge of 0. They weigh the same amount as a proton, 1 AMU. Together, the protons and neutrons in a nucleus give the atom its atomic mass, or atomic weight. The protons by themselves give the atom their atomic number. It's the number of protons that tells you how the atom is going to behave. For example, hydrogen has just 1 proton. That's why it behaves like hydrogen. That's why it's a gas. That's why it's highly flammable. Whereas oxygen has an atomic mass of 8, which gives it its characteristics that make it valuable for us to be breathing. Now, around the outside of the atom are the electrons. The electrons have a charge of a negative charge, and they're small enough that for the purposes of this class, we're going to say that they have no mass. They circle the nucleus, and they are what gives the atom its chemical properties, how it behaves when it gets with other atoms. In this next section, we're going to talk about bonds and attractions. We're going to talk about ionic bonds first, then covalent bonds, of which we have two types, nonpolar and polar. Then we're going to talk about hydrogen bonds and hydrophobic interactions. In this slide, we're going to talk about ionic bonds. But before we do that, let's talk about the arrangement of the electrons around the nucleus. We only have to worry about 3 orbitals. They're represented by these lines around the nucleus. It's kind of like satellites orbiting a planet. And for this class, we only need to worry about the first 3. Now, you'll notice this first orbital is kind of small. Only 2 electrons will fit in that first orbital. In the next 2 orbitals, 8 will fit. And all atoms, if you want to give them human emotions and wants, want to get up to full orbitals. It's kind of like playing 21. The closer you can get to 21, then you're closer to winning. You're more likely to win. So let's take sodium for an example. This figure represents sodium. It has an element number of 11, which means it has 11 protons represented by this green nucleus. Now, around the outside, we can get 2 electrons to fit in this first orbital, and it's full. Then we have 8 electrons in the second orbital, and it's full. Then we have 1 left over. We've got 1 electron in this orbital, and that's not really a comfortable situation, okay, because sodium's not going to go out and get 7 electrons. It's just not going to happen. Now, over here we have chlorine. Chlorine has an element number of 17. That means that it has 17 protons represented by the yellow nucleus. Now, in the center, we have 2 electrons in the center. Okay, that orbital's full. We have 8 electrons in the second orbital. That orbital is full. Then we have 7 electrons in the third orbital. It just needs 1 more. Okay. Now, the more stable configuration would be for sodium to lose that extra outside electron and for chlorine to pick up 1. So what happens is chlorine takes that extra electron from sodium. Now, it has one more electron than it has protons. That means it has a negative charge. Sodium has one fewer electrons than it has protons. That gives it a positive charge. Okay? Now, anytime an atom has either more or fewer electrons than protons, we call it an ion. Okay? So an ion is an atom that has a different number of electrons than protons. Okay? Now, positive ions are attracted to negative ions. Okay? They hang out together. Those charges attract each other. Okay? Here's another way to think of it as a schoolyard example. Big old mean chlorine is come and beat up poor little sodium and has taken his lunch money. Okay? So now chlorine has more money than it should, and sodium kind of follows around, hoping that he's going to get his money back. Okay? Now we have a name for the different types of ions. A positive ion is called a cation, and a negative ion is called an anion. Let's talk about atoms that are kind of medium-sized. They're not big enough to steal from other atoms, and they're not small enough to be giving up electrons to other atoms. Let's take hydrogen for an example. It actually is quite small, so it fits in the can be stolen from category, but it has an atomic number of 1, it has 1 proton, and it has 1 electron. Now it would really like to have 2 electrons in its outside orbital. So what it does is it gets together with another hydrogen and they share the electrons. They go zipping around both protons. We call this a covalent bond. Okay. And we represent this as a single line between the letter that designates the element. Or we can show it this way, with the lowercase 2, indicating that there are 2 hydrogens. Okay. Let's look at when we are combining atoms that are different. For example, carbon has an atomic number of 6. So we have a full electron orbital around the inside, and we've got 4 on the outside. Now, carbon would like to have 4 more. It's big enough, it's not going to give up those 4 electrons, but it really can't take 4 electrons from another atom. So in this case, 4 hydrogens got together. Remember, they want to share one, and they get together with carbon, and each hydrogen is forming a covalent bond with the carbon. And this produces methane, also known as swamp gas. You'll notice here we're showing a single line to show where each pair of electrons is being shared. Let's talk about water. Water, as you may know, is 2 hydrogens bonded to an oxygen, H2O. Oxygen has an element number of 8. That means it has 6 electrons in its outside or valence electron shell. It wants 2 more electrons. Hydrogen wants 1 more. So the 2 hydrogens get together with the oxygen and shares with the oxygen. Now, because oxygen is bigger than carbon, it can keep the electrons a little bit longer instead of stealing them. And so what happens is the electrons zip around hydrogen once, twice around oxygen, once around hydrogen, twice around oxygen, once around hydrogen, twice around oxygen, so that what happens is the molecule gets a slight positive and negative charge. Oxygen gets a slight negative charge because the electrons are spending more time around the nucleus of the oxygen, and the hydrogens get a slight positive charge. We call this a polar covalent bond. Think of it as the poles of the Earth. The Earth is a big magnet, and it also has a negative pole and a positive pole. Now, because water has a positive and a negative side, if you will, positive and negative pole, it forms bonds with other water molecules. The negative oxygen is attracted to the positive hydrogen, and so on and so on. And we call these hydrogen bonds. Don't get confused between the bond, the covalent bond, the nonpolar covalent bond between 2 hydrogens in gaseous hydrogen, and the hydrogen bond between molecules. Now, hydrogen bonds can form between any molecules where there is a hydrogen bonded to an oxygen or a hydrogen bonded to a nitrogen. Those are the ones that you need to worry about for this class. Now let's talk about what happens when you mix water with molecules that are not capable of hydrogen bonding. Here we have an example of a string of carbons, non-polar covalent bonds between the carbon and the hydrogens that are attached to it. And we have a bunch of waters. Well, the waters, because of their polar covalent bonds, they've got the slight positive and slight negative charges. They're attracted to each other. So this one comes over and says, hey, I can form a hydrogen bond with you, and it's all happy. And this one over here is saying, oh, well, don't leave me out of the party. And the carbon molecule is saying, hey, you're stepping on my toes. And it keeps getting more and more crowded. Hey. And it can't form hydrogen bonds with the water because it doesn't have an oxygen bonded to a hydrogen, nor does it have a nitrogen bonded to a hydrogen. So what happens is it's excluded by the water. Now we call this hydrophobic interactions. Molecules that are incapable of forming hydrogen bonds are excluded by the water that wants to hang out by itself. Okay? Kind of sounds like cliques in high school, doesn't it? Now, molecules that can form interactions, hydrogen bonds with water, are called hydrophilic. Philic meaning loving, hydro for water. So they're water-loving molecules, whereas molecules that are excluded by water, that can't hydrogen bond, are called hydrophobic or water-fearing. In our last section, we're going to talk about chemical reactions. Under this heading, we're going to talk about the various reactions that can happen, the fact that reactions in biology or microbiology are reversible, and the energy that are in chemical reactions. Let's talk about the various reactions. Say, for example, we have molecule A or atom A combining with atom B. Now that's probably pretty abstract. Let's talk about hydrogen gas being combined, and we'll call that A, and have B be oxygen gas. And if we combine those to make water, that would be considered anabolism, okay? Or putting two atoms, in this case 3 atoms, or molecules together. Okay, so anytime you take two different things, combine them together to make one bigger thing, that's anabolism. And that requires energy. Believe it or not, to make water out of hydrogen gas and oxygen gas, it takes energy and usually involves an explosion. Now, say we're taking something and we're breaking it apart. Okay, say we take water and we break it apart into oxygen and hydrogen gas again. Although that's not a really good example. We will have far more examples later. That is called catabolism. Think of it as catastrophic. Taking something bigger, like a building, and breaking it into smaller parts, the bricks of the building. Catabolism releases energy. And then there are the situations where we have two molecules and we switch the parts. For example, in this situation we have molecule AB and we have molecule CD, and we switch the B's and the D's to get AD and CB. That would be called an exchange reaction. Okay. Now, most reactions are reversible. So, say for example, that with molecule A and B, when we put them together to make AB, we can turn around and move it back. Okay. Most chemical reactions in cells are reversible. Inorganic reactions, usually they're not reversible, not unless you put a whole lot of energy into it. Now, let's also talk about some terms that you're going to need later. On this side of the reaction, we call these let's call these reactants. We have the two molecules that are going to be reacting. We put them together to make the product. Now you'll notice that if we're going this direction, this would be the reactant, these would be the products. Now let's talk about energy. Energy is the ability to affect change. Oftentimes we refer to it as the ability to do work. Kinetic energy is something we're familiar with. If you're running along, you're exhibiting kinetic energy. You're using the motion of your muscles to move you along. Or let's go with an inorganic example. If there is a boulder rolling down a hill, then it has kinetic energy. Now, before it started rolling down the hill, when it was at the top of the hill, it had potential energy. It had the potential to do work. Now, once it gets to the bottom of the hill, it stops and has potential energy again, but it has less potential energy than it had at the top of the hill. Chemical reactions are like that boulder. You can start out a reaction with lots of energy, go through the reaction, release energy, and have less energy at the bottom or at the end of the reaction. Now, we often graph this like this, where we have time at the bottom, we have the energy at the top, we have the reactants at the beginning and the products at the end, and you can see that in this case the reactants after the reaction released this much energy and we have less energy at the bottom. This type of reaction we would call exergonic. Okay. Now you'll notice that I skipped the hump here. It takes energy to break covalent bonds. Remember, those atoms are sharing electrons and they don't want to stop sharing electrons. You have to put energy into the system to get the atoms far enough apart that they are no longer sharing those electrons. We call this the energy of activation. Okay. Now we'll be talking about this later when we talk about enzymes because they lower the activation energy. Now, what if we were to go the other direction? What if we were to take molecules down here, smaller molecules, and we put them together to make a bigger molecule that has energy stored in it? We've added this much energy. That would be considered an endergonic reaction. Now, from the reactions that we talked about in the previous slide, which ones would be exergonic? Those would be the catabolic reactions. Those that are endergonic or require energy are the anabolic reactions. Alright, that's enough for this part of the chapter. Remember, I'm doing this PowerPoint in two parts. For part 2, we will be discussing water and organic molecules. Now remember, you have a quiz to take at the end of this PowerPoint.